Welcome to Engineering Out Loud. This is the first episode in our series from Mecasol's MESP Engineering Development Program, and today we're talking manufacturing and production.
I'm excited to get started.
To apply to the program, visit mecasolco.com/CPD. Okay, so let's dive into this amazing world where we make things.
It is a pretty amazing world.
I'm talking about everything from your phone to bridges
Yeah.
to even spaceships.
Yeah.
It all starts with manufacturing.
Absolutely. It's really the foundation of our modern world, isn't it? Transforming those raw materials into all the products we use.
Exactly, and the processes involved are just fascinating. We can't cover every single detail, but
Right.
we're going to explore some of those essential ones today. We're ready to roll up our sleeves.
Let's do it.
All right, let's begin with casting.
Okay.
To me, it feels like the most fundamental process. I mean, melting things down and shaping them
Yeah.
doesn't get more basic than that, right?
You're right. Casting is definitely one of the oldest and most versatile manufacturing processes.
Yeah.
There are a lot of different techniques, but we can think about them on a spectrum.
The spectrum. Okay, I like where this is going. Tell me more.
So on one end, you've got sand casting.
Okay.
It's like the workhorse of the industry. It can create almost any shape you can imagine.
Wow.
Yeah, you can make massive engine blocks or even intricate sculptures.
Really? So how does that actually work?
Well, it involves creating a mold out of sand.
Okay.
You pour molten metal into that mold, let it cool, and then you break away the mold and you've got your final product.
Interesting.
It can be a little rough around the edges, but it's incredibly flexible, especially for those larger parts.
So it's perfect when you need something big and strong, but maybe not perfectly smooth. What about when you do need precision? What do you do then?
Well, that's where die casting comes in.
Okay,
It's on the other end of our spectrum.
got it.
And it's all about precision and high volume. Imagine making thousands of identical, tiny, intricate parts, like the ones inside your phone.
Wow, that is a contrast. So how do they actually pull that off?
Well, die casting uses reusable metal molds.
Okay.
So you can create high-quality parts at incredible speeds. The level of detail you can achieve is really remarkable.
It's like comparing a blacksmith's forge to a high-tech microchip factory.
There really is.
Now, you can't melt just anything right.
Right.
What kind of materials are used in these processes?
That's a good point. So sand casting typically uses metals like iron, steel, aluminum, bronze. Think of those heavy-duty materials.
Makes sense.
Die casting, on the other hand, usually uses non-ferrous metals like aluminum, zinc, magnesium, and their alloys.
Okay.
Those are ideal for intricate and precise parts.
Interesting. So the material really dictates what you can make. What about investment casting? I've heard it's almost like an art form.
Yes. Investment casting, also known as lost wax casting, is a very specialized process.
Uh-huh.
So it all starts with a wax model of the part,
Okay.
and then that's coated with a ceramic material to make a mold.
Oh, wow.
Then the wax is melted out, leaving a cavity, and then molten metal is poured in.
So the wax is just temporary.
Exactly. Once the metal cools and solidifies, the ceramic mold is broken away, revealing this highly detailed and precise metal part.
It sounds like the perfect blend of craftsmanship and engineering. What kinds of things would you make of this method?
So investment casting is best for parts that need both intricate details and high precision.
Okay.
Things like turbine blades for jet engines, delicate medical equipment, even fine jewelry.
Wow. The range is incredible. From rough engine blocks to delicate jewelry, it seems like casting really can do it all.
It really can. It's a very versatile process.
And if all this talk about shaping metal is getting you excited about a potential career in engineering,
Yeah.
remember to visit mecasolco.com/CPD and explore the MESP Engineering Development Program.
It's a fantastic opportunity to dive deeper into all these processes.
Now let's move from shaping molten metal to shaping solid material. What about machining?
Okay.
It seems like that's all about precision.
You're exactly right. Machining is the process of removing material from a workpiece using cutting tools to achieve a specific shape and size.
And there are so many different ways to do it. Turning, milling, drilling, grinding. It's a whole toolkit for shaping metal.
It is. It's very versatile.
What exactly happens when something is turned?
So turning is kind of like sharpening a pencil, but for metal.
Okay.
The workpiece rotates while a cutting tool moves along its length, removing material to create a cylindrical shape.
So that's how we get those perfectly round parts like shafts and spindles.
Exactly.
What about milling? How's that different?
So in milling, the cutting tool rotates and moves across the workpiece
Uh-huh.
to create a wider variety of shapes. We're talking slots, grooves, flat surfaces, even complex 3D contours.
So milling seems like it would be used to make more intricate parts than turning.
You got it. We see milled parts everywhere, from engine blocks and gears to complex molds and custom parts.
Then there's drilling. That one seems pretty self-explanatory. Correct.
Yeah, drilling is pretty straightforward. It's all about creating holes, and you see it in everything from construction to electronics.
Makes sense. And finally, we have grinding. I've always wondered how those metal parts get those super smooth finishes. Is that grinding?
Yes, grinding is like the finishing touch in machining.
Huh?
It uses abrasive wheels to remove tiny amounts of material, creating incredibly smooth and precise surfaces. Grinding is often the last step for gears, shafts, and other parts that need to fit together perfectly.
Wow, so many ways to shape metal. Turning for cylinders, milling for intricate shapes, drilling for holes, and grinding for that perfect polish.
It's all about precision and craftsmanship, creating the building blocks of our modern world.
It really is amazing. Stick with us as we delve into the world of forming, molding, and joining after a short break. And don't forget to visit mecasalco.com/CPD if you're interested in learning more about the exciting world of engineering.
It's a great place to start. Now that we've covered some of the ways to shape metal by removing material, let's talk about forming. This is how we bend and shape materials without taking much away.
Forming, it sounds almost like we're playing with clay. But I'm guessing it involves some serious engineering too.
Absolutely. Let's start with forging. This process goes back centuries. Think blacksmiths hammering hot metal. Today, though, forging is also a high-tech process for making incredibly strong parts for things like jet engines and cars.
So forging has really stood the test of time. Why is that? What makes it so special?
Well, forging uses force to shape the metal. And this actually changes the internal structure, making it stronger and more resistant to fatigue.
It's like giving the metal its own set of muscles.
Exactly.
I've also heard of rolling. How does that compare to forging?
Rolling is all about taking large pieces of metal and squeezing them between rollers to reduce their thickness.
Okay.
Creating sheets or bars, these are the building blocks for so many things: cars, planes, even skyscrapers.
So forging is for shaping individual parts, while rolling creates the raw material for other processes.
Exactly. Another fascinating forming process is extrusion.
Extrusion.
Imagine squeezing toothpaste out of a tube, but with metal or plastic.
Okay, I can picture that. But how do you get those complex, consistent shapes, like window frames or pipes?
The key is the die.
The die.
It's carefully engineered to create that desired shape, and the material flows through it under pressure, taking on that precise form as it comes out.
It's amazing what a little pressure can do. And what about stamping? Is that kind of like a giant metal cookie cutter?
You got it. Stamping uses a press to force sheet metal into a die, creating a specific shape. This process makes everything from car doors to those little tabs on soda cans.
Stamping seems perfect for mass production, turning sheets of metal into tons of identical parts. What a variety of ways to shape metal. We've forged, we've rolled, we've extruded, and we've stamped.
Each one has its own unique strengths. Now let's move on to molding. We touched on it a little bit with casting, but this time we're focusing on the world of plastics.
Plastics are everywhere. But isn't molding as simple as just making a mold and pouring plastic in?
Well, there's actually a whole family of molding processes, each with its own special capabilities. We've got injection molding, blow molding, compression molding, rotational molding, thermoforming. The list goes on.
That's more than I expected. Let's explore at least a few of those just to kind of get a sense of the possibilities.
Absolutely. Let's start with injection molding.
Okay.
This is the workhorse for making plastic products. Think intricate Lego bricks to complex car parts.
Wow.
So plastic pellets are melted and injected into a mold under high pressure. The plastic cools and solidifies, and there you have it.
So it sounds a lot like die casting, but with plastic instead of metal.
Right. Now let's look at blow molding. This is how we get all those plastic bottles we use every day.
Oh, interesting.
So a heated plastic tube, called a parison, is clamped into a mold and air is blown into it, inflating it like a balloon until it takes the shape of the mold.
I can actually see that. What about those thicker, more durable plastic parts? Things like tool handles or electrical components. How are those made?
That's where compression molding comes in. A chunk of plastic is heated and then pressed into a mold, squeezing it into shape.
Okay.
Perfect for those sturdier items.
Okay, what about those really big plastic items? like kayaks, storage tanks, or even playground equipment. What's the secret behind those?
Those are often made with rotational molding.
Rotational molding.
Plastic powder is placed into a mold, which is then rotated in multiple directions while being heated.
Oh, wow.
The powder melts and coats the inside of the mold, creating a seamless hollow part.
It's amazing how many different approaches there are. And this is all just for plastic. What about thermoforming? I've heard that term, but I'm not sure what it is.
So thermoforming is all about shaping plastic sheets. A sheet of plastic is heated until it's pliable, and then it's either sucked onto a mold using a vacuum or pressed onto a mold using pressure.
Okay.
This process is used for all kinds of things, from packaging materials and blister packs to even car dashboards and refrigerator liners.
It's incredible how many everyday objects rely on molding. It
Yeah.
really highlights the impact of this one manufacturing process.
It's true, and we've only just scratched the surface.
Right.
If you're finding all this as interesting as I do, be sure to visit mechasalco.com/CPD to learn more about the MESP Engineering Development Program.
It's a great opportunity to explore the world of manufacturing in more detail. We've cast, we've machined, we've molded. Now it's time to put all the pieces together.
Right.
Let's talk about joining. What are some ways to ensure those parts stay connected?
Well, joining focuses on creating those reliable connections between different components. And the techniques are really diverse, ranging from the heavy-duty strength of riveting and welding to the more delicate approaches of soldering, brazing, and even using adhesives.
Let's start with those heavy-duty options. Riveting. That sounds pretty intense.
It is. Riveting is all about those classic metal fasteners, rivets. We see them everywhere. Bridges, airplanes, you name it. A rivet is inserted through holes in the pieces being joined, and then the end of the rivet is deformed to create a second head, locking everything together. It's incredibly strong and reliable, especially for large structures that need to withstand a lot of stress.
So riveting is a purely mechanical way to hold things together. What about welding?
Welding uses heat to melt and fuse metal parts together. It's a core process in so many industries.
There are so many different types of welding. MIG, TIG, stick, flux core. What are the key differences between them?
Okay, let's break it down. MIG welding, which stands for metal inert gas welding, is known for its speed and versatility. It uses a continuously fed wire electrode and a shielding gas to protect the weld from contamination. You see MIG welding used in everything from automotive repair to heavy-duty construction.
Sounds like MIG welding is a good all-around process. What about TIG welding?
TIG welding, or tungsten inert gas welding, is all about precision and control.
Okay.
It uses a non-consumable tungsten electrode to create the weld, and it's perfect for fine and delicate work. TIG welding is often used for welding thin materials or in applications that require exceptional weld quality, like aerospace or high-performance racing.
And then there's stick welding. It seems like the classic, rugged type of welding.
That's a good way to put it. Stick welding, or shielded metal arc welding, is a very versatile and portable process. This is why it's still so popular in construction and repair work.
Yeah.
It uses a consumable electrode coated in flux, which creates a shielding gas as it burns, protecting the weld.
So stick welding is perfect for tough outdoor jobs. What about flux core welding? How's that different?
Flux core welding is similar to MIG welding in that it uses a continuously fed wire, but in this case, the wire is filled with flux, which creates the shielding gas. It's a great option for welding thicker materials and for situations where a shielding gas might be blown away, like in windy conditions.
Okay, so we have the powerhouses of joining, riveting and all those different types of welding. What about soldering and brazing? Those seem like they're for more delicate tasks.
You're right. Soldering is a lower temperature process that's often used to join electronic components, plumbing parts, and other smaller items.
Right.
It uses a filler metal called solder, which has a low melting point to create the joint. Brazing, on the other hand, uses a filler metal with a higher melting point, creating a stronger and more heat-resistant joint. Brazing is common in automotive and aerospace applications where parts will be exposed to higher temperatures.
It seems like there's a specific joining technique for every situation. And then there's adhesive bonding. It sounds so simple. Is it really that high-tech?
Modern adhesives are incredibly sophisticated. They can bond a wide range of materials, from metals to plastics to composites, and they can create extremely strong and durable joints. We see adhesive bonding everywhere, even in building airplanes and assembling smartphones.
It's incredible how something that seems so basic can be so important in high-tech manufacturing.
It really highlights how innovation can transform those simple concepts into powerful engineering tools.
We've covered a lot of ground in this deep dive, from melting metal to gluing it all together. It's amazing to see how these processes shape the world around us.
It truly is a testament to human ingenuity and our ability to create all the products we use every day.
And it's just the beginning. With new technologies like 3D printing emerging all the time, it's exciting to think about the future of manufacturing and what we'll be able to create. If you want to be part of this exciting world, I encourage you to apply to the MESP Engineering Development Program at mecasolco.com/CPD. It's a great way to learn more and start your engineering journey.
And who knows, you might even discover your future career.
Thanks for joining us on this deep dive into the world of manufacturing and production. We've barely scratched the surface, but hopefully this has given you a taste of what's out there.